In this video, I've decided to revisit a simple simulation in R that I like, the snake eyes simulation. I think I like it because it gives a distribution that's not normal, and then got a very long tail, it's skewed, everything that's sort of not normal. And I want to look at it further in this video to sort of say that sort of fluctuations around. So if I get that sample and then I run several samples of that sample and run statistical measures, then those measures in the sort of sample of samples that can be or often is normal. So here's the original simulation. Start down here in the while loop. I'm using sample. I'm taking a sample between the variables or the values 1 and 6. I'm getting 2 of them, and I'm allowing replacements. So this is the simulation of rolling 2 dice. I'm getting 2 numbers between 1 and 6. Then I'm summing them. So that's the adding of 2 dice. And I increment a counter. So every time I roll the dice, I increment a counter. And I continue while I haven't got the snake eyes, while my sum is not equal to 2, I continue. And then I keep track of how many rolls it took. And so I have, in this case, 10,000 samples. I set up a vector for how many rolls. And I performed down here, that's a histogram of it. So you see this very long tail. I did a summary. You see that down here in the console. You see that the median and the mean are not the same, so it's skewed. I calculated the standard deviation. It's quite large. And let me uncomment the box plot, and we'll see that there are lots of outliers. So here's the top of the normal box and whiskers, and then here is a large collection of outliers. So it's very much not a normal distribution. Okay, now I want to look at, so I still have the basic, here's that basic simulation of doing that. I start off with rolls, I go over the sample size, I have my loop inside, I get the count of the number of times I rolled 2 dice before I got snake eyes. But that's inside another loop. And this is a smaller size of 50. In this case, I reduced my sample size to 8,000. And so I do that simulation I just showed you before. And now I'm doing that simulation 50 times over. And I'm calculating, and this time the vectors I'm keeping track of are, I get, for one of my samples, I get this distribution rolls that I showed you in the other case, that very wide, long tail distribution. And I'm taking several statistical measures of that distribution, the mean, standard deviation, the skewness, and the kurtosis. And I am sort of collecting them each in a vector. And then down here, I showed the distribution of the averages and a summary statistics of the averages and a standard deviation of the averages. And so we see here so we had this distribution that was not very normal, not at all normal. And now we took some basic statistical measure of it, its average, and then we performed the simulation a number of times over and looked at the statistics of the sort of statistics of the statistics. And we see that this is more like a normal, a peak in the middle, the median and the mean are close. We've got a standard deviation. So we've got also sort of a hump, something more normal. And I looked at that was the averages. Let me look at the standard deviation. So I'm doing Control-Shift-C to uncomment them, and I'll run the standard deviations. And there again, it's sort of peaked in the middle. The median and the mean are close. Let's do skews, Control-Shift-C. Run that. Sort of not quite as nice, but still median and mean close. And the Kurtz, usually this has been not as nice for me. Control-Shift-C, run that. And that's still a little bit all over the place. So though the median and the mean are close, so at least it's there's a bit of a tail, but it's not so skewed, and it's got still a fairly wide standard deviation. Okay, what else do I want to say? I'm not running this for you because it's the while loop can take up to 300 steps, and then there are like 8,000 of that and samples of that, and then 50 more samples of the samples. So it takes a little while. So I'm just showing you some results I have, one instance. Now, I did one more thing. I took the averages and I took the standard deviation of the averages. So how spread out are the averages? And I looked at that as a function of this sample size. I was varying the sample size. So how much is our measure of the average? How spread out is that as a function of the sample size? And usually in statistics, they tell you that this goes like the square root, the inverse square root of the sample size. So that's what I wanted to sort of look at here. One was this distribution. First was this distribution that was not normal. Were the fluctuations about that non-normal distribution normal? And it looks like they are. And then is this dependence on sample size sort of, a reciprocal square root to the -1/2 power? So I did 1,000, sample size of 1,000, and grabbed some standard deviations of my average. So how spread out was my average when I had a sample size of 1,000, sample size of 2,000, 4,000, 8,000. And here I have collected that data as it sort of ran. Then I sort of wrote it down over here in Excel, and I have made a plot of that, again, the spread in the averages versus sample size, and fit that in Excel to a power law, and increase this. It's probably hard to see. I'm getting that it depends on sample size. I'm getting a power here of -0.45. So hopefully if I did bigger sample sizes and ran more runs, I would see the sort of -0.5 that statistics normally talks about. Okay, that's what I wanted to show you. Probably more about statistics than R, but that's appropriate enough since R is so often used to do statistics. All right, thank you for your attention.